Hi and welcome for the second part of two videos about specific heat capacity and the coefficient of linear expansion. So today we're going to talk about the coefficient of linear expansion. Coefficient of linear expansion is all about how much the material expands by when it's heated. Now, as you well know, we have three common use materials for pipework. We have LCS, which is low carbon steel. We have copper, which is common use in the domestic properties, and we have polybutylene, which is again common use in the domestic properties for pipework. All of these three materials expand in the different rates. So whether the rate of expansion is caused by a sunlight shining on it, or whether it's caused by a warm hot fluid through it, the pipe will expand. Likewise, guttering outside of the property will expand the same. Plastic guttering expands more than any other material you use as a plumber. So, I have a table here about coefficient linear expansion of materials. As you can see, we've got plastic, we've got lead, we've got copper, we've got cast iron. All of these values is given to us, so this value is not going to change. Okay, we need these values to use later on to work out our examples. Okay, there's more materials than that, but we're using these values. All right, so as you can see, plastic expands far more than any other material. Okay, so therefore all the manufacturers will work with us to help us to use some fittings to allow the pipework to expand. So if you go back to our guttering fittings, as you well know, is got an insertion point where your pipe should stop. Now then, if you engage the pipe all the way through the fitting, right, you don't allow any room for expansion. So therefore, the pipe becomes buccal. Now, what you need to do is make sure you engage the pipe to the insertion point, and it gives you a 10 mm gap to allow the pipe for expansion. Likewise, the polybutylene pipe, before you inserting the pipe into a fitting, you normally on the end of the pipe, you pull a pipe sleeve or a pipe insert. Okay, this pipe sleeve and pipe insert is not only to helping you with the watertight, is also to allow the pipe to stay in place and to allow to expand over time. Okay, so there is three criteria points you need to take in consideration. First, we need the coefficient of linear expansion value for each material. It could be either LCS, copper or plastic. Always refer to the table. Okay, so we need that. We need this value for us to work our example later on. All right. The second part is you need the overall length of the material. So you need to measure. Now, there is one particular part you need to remember. When you measure, you normally measure in meters. But when you're doing your calculations, you need to be able to convert to millimeters. Okay? So our final workout will be in millimeters. All right? And the final part, or the third point, is a temperature rise. As you remember from the first video, right, the temperature rise, to work out the temperature rise, is from the start temperature to the final temperature. You have to take both away to identify that temperature rise. So when you are doing your calculations, you maybe will need to take the start temperature from the final temperature to get your temperature rise. Okay, now then, I go in an example here, right? I hope you can see it. So I got an example here, but calculate the increase in length of 6 meters long plastic discharge stack that is subject to a temperature rise of 19 degrees. Okay, so as you can see, when you're giving you a question like this, you might be thinking, wow, I don't understand much of these. Now then, I underline what is more important. Okay, so you need the length. So the length is 6 meters. You need plastic. So plastic is our material. You need the temperature rise, which is 19 degrees. Now, this is a good technique when you learning through your before your exams, or if you're learning through your worksheets. Just underline the key areas, which is helping you to understand the question properly. Okay, so we have the length, 6 meters. We have the plastic, we have the temperature rise, and you got our value, right? So now if you go back to our table, so we need plastic, so plastic is 0.018, so that is the coefficient value. So now let's go back to our formula, right? So we have our formula. Now then, I got two formulas here, okay? So the first one is for more advanced formula for you to work out the temperature, the different temperature, the temperature rise. So we got the length times the coefficient value and the first two temperatures, which is you take it away from it. For today's exercise, what you need is the length times the temperature rise times your coefficient value. So, which is 6 meters, okay, which is our length. The temperature rise is 19, so 6 times 19 times your coefficient value. Always refer to the table, which is I'm looking for it. So the table, which is 0.00018. Okay. Now then, after you times all them together, right, it gives you a value. Now, some students got a problem with this. All right. Then this is why we have to refer to maths. Remember your decimal point. So you need to move your decimal point across. Right. So which is gives you 20.52 millimeters. Okay. So that expansion is about 20.52 millimeters, right? Now then, what you need to do is practice. The more practice, the more you become better and the more you understand it, okay? This is a good stepping stone for your rest of the units. Could be either hot water, central heating. You need to know the importance of the materials you are about to install. I hope you found this video helpful and informative, and I hope to see you soon.